Okay, so welcome back, everybody. Um, so I was having audio issues, and hopefully that's not the case now, and hopefully those are kind of ironed out after fixing it over the weekend. Seems that it's come back somewhat, but hopefully it's not a fatal flaw here. So just let me know if there's anything wrong with the audio, and I will try to fix it. But anyway, tidying up some of the last stuff from chapter 2. Our last topic from chapter 2, and the last major topic from chapter 2 was Laplace transforms. That was definitely the last major topic. This was kind of a collection of, well, it's one topic, but it's from a couple of different sections, and this is not as important. It's not really going to give us a new way of doing anything. And this is Green's functions. So I wanted to introduce these. There's a couple of reasons. So one, this provides an alternate way of thinking about how to deal with some of these non-homogeneous problems. But also, it provides an easy way to generalize um, the method of variation of parameters to higher order equations. So the formula that we had for variation of parameters is not something that easily generalizes in that form to higher order equations, right? We did it for second order equations and then we didn't talk about it anymore. But if we put it in the Green's function form, this actually easily generalizes to higher order equations. So that's the point. That's the deal here. What is a Green's function? The idea here is as follows. So suppose that I have a constant coefficient differential operator. So L is a differential operator of some order, has constant coefficients, and consider the equation Ly is equal to f of t. Right, so Ly is equal to f of t here. Right, so L is the operator d to the n plus a1 d to the n minus 1 and so on all the way to a n minus 1 d plus a sub n. Yeah. So here's L. These a sub i's are constant. These d's are the normal derivative operator. Okay. Um, so then what uh, what what do I do to solve this, right? Well, hopefully, right, if f is in characteristic form, I would use key identities or undetermined coefficients and be happy. But one, f might not be, but also what's another way of thinking about this? So it turns out that there is a particular solution that satisfies some initial conditions that we might find nice, and that is, so it turns out that if we seek a particular solution, say y sub p of t, that solves the differential equation first of all, so L of y equals f of t with initial conditions. So remember, typically when we are looking for a particular solution, we're just happy that it solves a differential equation. We don't necessarily care about the initial conditions that it would satisfy, right? So if you found a particular solution, right, you're looking for a single one, right? This is not a general thing in the same way that we say something's a general solution. We're looking for a single solution that makes this work. But say we have something that solves a differential equation additionally with IC's, so y of t sub I equals y prime of t sub I all the way up to y, or the n minus first derivative of y t sub I. Let's make all of those 0. Okay. So if we seek a particular solution that satisfies the differential equation and these initial conditions, then y sub p is given by the formula so this is y sub p of t is the integral from the initial time t sub I to t of g of t minus s times f of s ds. Now before I tell you what this g is, note that immediately this satisfies the first initial condition, because if I plug in the initial time t sub I here, this is the integral of from t sub I to t sub I, and it doesn't matter what this is, right? That integral is 0. Okay, so so what is this g, this little g of t? So notice I'm integrating with respect to s here, so s is my dummy variable. I'm integrating with respect to t is my actual this is the actual argument for the function. So that's here and here, showing up in this t and this integrand here. F, of course, is the forcing function, the right-hand side function, little f. Okay, what else? Well, this little g, is determined by the following. So where g is a solution of the homogeneous problem, this is the homogeneous IVP, that is LG equals 0 is the differential equation. So it is the same differential operator L as for the original problem here. There's my original differential equation. Here, this is the associated homogeneous problem here, but I'm going to impose initial conditions here that I impose to find that particular solution. So here, my initial conditions are g of this initial time I'm going to take to be 0, actually. So it doesn't matter what this t sub I is, this is still going to work here. So this is a g of 0 is 0. G prime of 0 is 0. And so on, all the way up to the n minus second derivative is going to be 0. But that last IC is going to be different. The n minus first derivative of g is 1. So all these initial conditions are zeroed out, except this one is 1. Okay. So if g is the solution to this thing, all right, so we would solve this homogeneous equation with all these initial conditions imposed. Solving a linear homogeneous equation is easy. That's just finding the roots of the characteristic polynomial. Right, so finding roots of the characteristic polynomial, let's say that I've already done that. I impose these initial conditions. That gives me g that solves this. I then use that in this formula to write out my particular solution. Now, a couple of things to note here. One, this would work even when f is not in characteristic form. Okay, so this works even when f is not in characteristic form. And two, we'll see that this is really variation of parameters, except it's hiding Now, as I said, there are some useful reasons for why to deal with this Green's function. Like the Green's functions have certain properties that make them really nice. And there's a lot that you can do with them, so it does make sense to treat them slightly differently from variation of parameters, but really just know that variation of parameters is what's going on here. So it's not really a new thing. It is actually just variation of parameters continuing on under the banner of Green's functions. Okay, so I'm not going to do an example of this. Rather than doing that, I'm going to show you how variation of parameters leads directly to this. Um, so the this whole discussion takes place. Let me go back really quickly. Let's see here. So this whole thing takes place starting on page 31 of chapter 2, section 6. But really, page 31, 32 is where the meat of this discussion happens. All right. But the seeing how it ties in with variations of parameters happens in the next section. So this is chapter 2, section 7. So then how does the Green's function approach work for variable coefficients equations? So let's see where this comes from. So now recall a second order variable coefficient problem can be solved via variation of parameters. Okay, so what does such a problem look like? So let's say we have y double prime plus a1 of t y prime plus a2 of t y is equal to f of t. Right, so there's our problem, right? Now remember, a kind of a unifying theme here was that the problem was to get started on this required that we knew the homogeneous solutions to this. So we needed two linearly independent homogeneous solutions to this. The issue with that is that we don't have a general method for constructing those things, right? So we don't have a general method for constructing a solution to the associated homogeneous equation here. So then what do? Well, we have to either be given them, right? Or just find them through some trial and error, right? Just already having found them. The other alternative, of course, is that you're applying this to constant coefficient problem. And the reason you're using this instead of undetermined coefficients or key identities is because f might not be in characteristic form, right? So that's also an option. Okay, and in that option, to find the homogeneous solutions, you would do the characteristic polynomial type analysis, right? That's where those would come from. Okay, so recall we seek, so this is just kind of a refresher, we seek a particular solution of the form y of p of t is u1 of t, y1 of t plus u2 of t, y2 of t, where y1 of t and y2 of t are linearly independent solutions, or a fundamental solution set. That's another way of saying this, where y1 and y2 are linearly independent solutions to the associated homogeneous equation y double prime plus a1t y prime plus a2t y is equal to 0. Okay. I.e., this has homogeneous solution, right? C1 y, C1 y1 of t plus C2 y2 of t. There we go. Okay. So here's the homogeneous solution. Again, we don't have a general method for finding this. We just have to be given it if these are honest to God functions of t. And here's my particular solution, my sub p. But recall that a way that we computed this using variation of parameters, right? So what was variation of parameters here? You can think of this as a good review. Variation of parameters told me I could compute this by computing two integrals for u1 and u2. So the first one, u1 of t, what is that? So u1 of t is computed by this integral minus the integral from t sub I to t sub I being the initial t here, okay, to or of y sub 2 of t f of t over the Wronskian of y1, y2, t dt. Well, I've done something wrong here. So I've done something slightly wrong. This is my variable. Here is where this goes. Okay. Then I need to replace the integrand with some dummy variable. So I'm going to replace this with the dummy variable s here. So here's s, here's s, here's s, and this is all ds. Okay. All right. So when we were doing this before, we wrote it as an indefinite integral, typically. Here, I'm just rewriting it as a definite integral. It's no different here. I'm going from the initial condition to t instead, so that what results here is going to fit in with the IVP that I wrote for the associated thing to Green's functions for constant coefficient equations. Okay, so this is u1. u2 of t can be computed by the same kind of integral as before. So this is from t sub I to t of y1 of s f of s over Wronskian of y1, y2 of s ds. So this is just the variation of parameters formula. Okay. And so here is the point. I want to take these two things, right? And if I recall that I want y sub p to be the thing that's of this form, where I've taken the parameters, the arbitrary constants, c1 and c2 in the homogeneous solution, and I have varied them, right? Hence variation of parameters. I varied them by considering these now as functions of t, u1 of t and u2 of t. Then this form the particular solution takes is going to be this u1 times y1 plus this u2 times y2. So if that is the case, then, and I'll leave these on the same page, then y sub p of t is equal to the integral, and now you'll see why I wrote these as, the integral from t sub I to t here. So this is the integral of t sub I to t of big G of t and s f times f of s ds, where big G of ts is what? It is going to be y1 times y2. Oh, here, let me pull this down. It's going to be y1 times y2 minus y2 times y1 over the Wronskian in both terms. So rewriting that, this is y1 of s times y2 of t. Let's be careful here. So this is going to be y1 of s times y2 of t. All right, so here's u2. y1 of s times y2 of t. Yep. Minus for the same reason. This is y2 of s times y1 of t. So I'm going to rewrite it as y1 of t times y2 of s all over the Wronskian of y1, y2 of s. Okay. A way of remembering this, and actually the way of seeing how this more easily generalizes, is to rewrite this as two determinants. This is the determinant of the matrix y1 of s, y1 of t, y2 of s, y2 of t, divided by the determinant of y1 of s, y2 of s, y1 prime of s, y2 prime of s. And this big G is called my Green's function. Now, a couple of things here. Before, it was not apparent how to take these two things for finding U1 and U2 and translate them into a method that would also allow you to do this for a third order problem, right? So imagine that I'll do it on another sheet of paper. So imagine for a second that I had something like this instead. So let's say I have something like this, so a third order variable coefficient equation, right? How would I apply variation of parameters? So the way that we dealt with higher order stuff, earlier was to basically take what we did in the second order case and just generalize it, and it was typically pretty easy to see how it generalized. So for instance, for homogeneous constant coefficient equations, the way that it generalized was if you could find all the roots, right? So assume that you could fully factor or find all the roots to some degree in polynomial. Then you were able to do this by just associating to each root whatever solution piece was supposed to be associated with it, right? So that's how we did this, right? That's how we were happy to generalize. But in this case of variable coefficients, I'm trying to generalize these formulas to this, right? And so how do I do that? It's not immediately clear how this is going to work from these formulas, right? Yes, it's true that if I had a fundamental solution set, now y1, y2, and y3, well, the Wronskian of these three things makes sense. So this would be a determinant of 3 by 3, right? So this makes sense. So I can immediately plug that in here, but how do I know what the sign is right? How do I know what goes here in these integrands? It's a little confusing if I'm looking at it this way. It turns out, though, that if I'm looking at it in the Green's function formulation, so here, then it's actually clear what's going on, because all I have to do is expand this determinant to be y1, y2, and y3, right? And so I'm going to expand this determinant. I'm going to expand this determinant, and that's going to be my Green's function. This f of s is going to be the right-hand side in any case, and that is going to be how this thing works. So this actually shows how to generalize variation of parameters using this formula. This looks, of course, like a single integral. We know that we split it up as two different integrals here typically, but this is our method of Green's functions generalized to variable coefficients and also generalized, like I said, to any order. So yes, this is specifically the formula for second order, But looking at this for third order only requires making these 2 by 2 determinants, 3 by 3 determinants, and adding in the y sub 3 here. And that's it. That's how you do this. Now, a quick question is, how does this relate to the previous Green's function thing? So how does this relate to the Green's function for constant coefficients? Right? Now we know that variable coefficients contain constant coefficients as a subcase inside them, because you could just pick those functions to instead be constants, right? So how do these things relate? Well, the Green's function method for constant coefficients led to this formula for the particular solution. Compare, right there. How are these two things related? Well, it turns out that big G of TS in this case is equal to little g of t minus s in the constant coefficient case. So that's how those things are related. Okay. Now, as I said, I'm not going to derive properties of the Green's function or do much other than to give you this formulation of these as arising as a kind of an alternative way of thinking about variation of parameters. But really, it's just variation of parameters. Okay. So if I ask you to compute the Green's function for a given problem, really that's me asking you to solve a variation of parameters problem, or to at least do enough work that's kind of equivalent to solving a variation of parameters problem. Okay, so that's it. That's all I wanted to say for the last remaining bit of Chapter 2 stuff that I wanted to finish up. Okay, so that's more or less the last thing I wanted to mention from Chapter 2. So then, what is kind of the thing that that we're going to focus on for the remainder of the course? So Chapter 3, this is our last third of the course. And what does it concern? It concerns first order systems of equations. Okay. So from now on, we are going to be dealing only with first order equations, but they are going to be systems of equations. So what does this look like, right? The idea here is that I have n first order equations. So I am solving simultaneously for n unknown functions. So I have a dx sub 1 dt is equal to f sub 1 of t and x sub 1, x sub 2, and so on all the way to x sub n. The second equation is the derivative with respect to t of x sub 2. That is equal to some second function which depends on t, x sub 1, x sub 2, all the way out to x sub n. Okay, and this goes all the way down to d x sub n dt is f sub n t x sub 1, x sub 2, all the way out to x sub n. So, rewriting these as a vector, right? So if x is the vector, and I'll write this as x of t here. If this is the vector containing the unknown functions x sub 1 of t to x sub n of t, and if f is the vector, So if f of tx is the vector that contains the right-hand side f's, so all these are being taken together. So a solution, or the solutions x of 1, x of 2 to x of n of this system would solve all of these simultaneously. This is my vector containing the right-hand side functions. I can rewrite this thing as the following. So now I can rewrite this equation in a easier form. This is dx dt is equal to ftx. Now, this might be a little scary to you, the way this is written up here, because it might not be clear, like what it is that's going on. Let's look at a particular example here. So, let's look at an example. So let me just say, let dx1 dt be equal to, say, like t squared minus 5x1 plus x2, and dx2 dt is equal to, say, 3x1 minus x2. Okay. All right. So then notice, right, the f here, the f vector, would just be the vector that contains the right-hand side. So the first entry would be t squared minus 5x1 plus x2. The second would be 3x1 minus 3x2. All right, so let's actually rewrite that real quick. So this is, and of course I could have, so here, let's do something a little nastier. My brain wanted to go with something that was nice inherently. So let's make this slightly nastier. Let's put a square there. And maybe let's put a cubed here. There we go. So then under this formulation, my solution vector x to this thing would be just x1, x2. So what am I doing? I'm seeking two unknown solutions, x of 1 and x of 2, that satisfy these equations. So what are these equations? Well, it satisfies so they're first order, because the only derivative showing up is the first derivative. X of 1, when you take its derivative, what you get is t squared minus 5 times x of 1 itself cubed, plus x of 2, which is the unknown solution to the second equation, which tells me that dx2, so when you take the derivative of x of 2, you get 3 times x of 1 minus x of 2 itself squared. Okay, so this is an example of a nonlinear system. Let me write out what f is. Oh, I wrote it as tx before, so let me do that. So this is simply, t squared minus 5 x1 cubed plus x2, and 3 x1 minus x2 squared, like this. Okay. So this is an example of a nonlinear first order system. Now, we will eventually talk about nonlinear first order systems, but we won't do this, so we won't handle these until the very end. till the very end of the course. So that for some reason my stream disconnected again, but it seems like it's back now. So yeah, let me know as long as it looks fine and didn't miss too much. This will. I didn't write too much while it was down, it seems, but it did look like it skipped a little bit on my screen, maybe like 10 seconds or something. I don't know. Anyway, so we're not going to handle this until the very end of the course. It's nonlinear. Why is it nonlinear? So this t squared has nothing to do with it being nonlinear. It's allowed to this t could be whatever, or the terms that it only involve t can be whatever. It's nonlinear because it's nonlinear in the x slots. So it's nonlinear on the unknown functions. Right? So it's similar to how we defined linearity when we were first talking about it when we were looking at first order equations, right? So this is a nonlinear first order system. So then what does a linear first order system look like? What does a linear first order system look like? So it turns out that a linear first order system looks like this. So it's dx dt is equal to a of x, or how should actually, I think the better way of writing this is, let's do linear first order system, and let's do this for constant coefficient. So what does the constant coefficient tell you about? So here, this equation was in fact constant coefficient because all of the constants on the x terms, or sorry, all of the things multiplying the x terms are constants. I could have had functions of t multiplying these, right? Constant coefficient here is going to refer to this matrix that I'm about to write out, a plus f of t. Okay, so this is my way of writing this in a nice way that's kind of easy to, or I should say is convenient for our purposes, where this x is the vector of solutions. Yep. And this f of t in this case is just a vector of right-hand side functions you can think about. And this matrix A is some n by n matrix. Now, in general, right, if I wasn't dealing with constant coefficients, then this matrix A would actually depend on t. But if I'm in the constant coefficient case, then it doesn't. All right. Now, for the rest of this course, we're going to be in the constant coefficient case always, but this is just letting you know, right, that generally I could have just a slightly more general equation here where this a of t would depend on t instead. So I'm going to choose for it to be a constant. What would an equation like this look like? So let's just see an example real quick. So an example here is, let's look at the equation. dx1 dt is equal to like 3x1 minus 5 x2 plus cosine t, and dx2 dt is x1 plus 3x2 plus t squared. Right. So that's a way of rewriting this in the way that I had it there. So this is actually dx dt which is A times the vector x plus f of t, where the vector x of t is my solution vector. So this is just the vector that contains the unknown functions x of 1, x of 2. Okay. So this is a vector containing the unknown solutions. Okay. The A here is what? A is going to be a 2 by 2 matrix. Turns out that if this is, let's go back here for a second. Turns out if this solution vector has n components, right, and just I wrote 2 here. This is n. So if the solution vector has n components, then what's the size of A? A is going to be an n by n matrix in that case. So here, since this is a system of 2 equations, my solution, my unknown functions I'm solving for, there's 2 of them. A is going to be a 2 by 2. Well, what is A? 3 minus 5, 1, 3. Why? Where do I get this from? Because A is multiplying x here, and x is the solution vector. So I'm looking, what is A times x? Well, this would be this matrix that I'm claiming it is, 3 minus 5, 1, 3, times the vector x1, x2. How do I multiply these two matrices? I'll do a review of some of this stuff in a little bit. How do I multiply these two matrices? What I would get here is a 2 by 1 column vector, 3x1 minus 5x2 in the first slot. So 3x1 minus 5x2, that's in the first slot. In the second slot, this is x1 plus 3x2. And notice that's exactly the pieces here, right? Of course, it's not the entire right-hand side of this equation. If I wanted that, this would be my vector f of t is the column vector consisting of cosine t and t squared. So now piecing these things together, a times x is 3x1 minus 5x2, x1 plus 3x2. I add to that f of t, which is cosine t, t squared. What do I get when I add those two together? I get a column vector that is, well, let's just do it. So this is a x plus f of t is 3x1 minus 5x2 plus cosine of t, and x1 plus 3x2 plus t squared. So this is the vector I get. But then the system of equations I started with is really a vector dx1 of t dx2 of t. Oh, but really this is just the derivative of the vector x1 of t, x2 of t, but that's my solution vector x. Okay, so this is showing how this shorthand way of writing this system works out exactly how you expect it. Okay. All right. So this works out perfectly. Now, we are actually going to restrict ourselves a lot more than this suggests. Okay. So this is known as, what kind of equation is this? This is a constant coefficient, and the reason it's constant is because this coefficient matrix A it only contains constants. Okay. This is called a constant coefficient. Linear. Really, linear should come first, but whatever. So it's linear means I can put it in this form, where this f is not just some general function that involves the x, it actually only involves t. This is non-homogeneous, and it's non-homogeneous because f is non-zero. So this f is not the zero vector. It's not zero in every slot. But it turns out that actually the thing that we're going to consider the most for this section is linear constant coefficient homogeneous, where f is 0. And I'm going to write one of those here in a second. So this A is called the coefficient matrix. So A is the coefficient matrix for the problem. Okay. Now, you might ask, like, what's the purpose of doing it this this generally? We are going to have an existence and uniqueness theorem. I'm not going to state it or prove it, but basically, if you have a reasonable system like this, there's an existence and uniqueness theorem that says that there exists a unique solution to an IVP, okay, of, say, this form, or of a form where these things are nice enough. Now, the IVP, right, like how do I impose an initial condition on this? Well, I have like a vector of initial conditions, right? These are all first order, so I don't have to worry about like conditions on the higher derivatives, but I do have to worry about conditions on each of these unknown functions. But that gives me a vector of initial conditions. So an IC for something like this looks like an imposition of saying that my vector x, the solution vector, at some initial time is some vector that I will call x super I. So I'm going to use superscript here. Okay. So let's do a quick example of that. Let me get some more paper. So quick example here. Dx1 dt is equal to, let's say, 2x1 plus x2. And dx2 dt is equal to 3x1 minus 4x2. Okay, and we'll say that we have an initial condition x of 0 is equal to the vector minus 1, 0. Okay, so putting this in the form that we were just looking at, this is rewriting this as if so x of t is my solution vector, so this is x1 of t, x2 of t, and in that formulation, the left-hand side can be condensed as dx dt, and that is equal to the matrix 2, 1, 3, minus 4 times the vector x1, x2. Rewriting this, if I call this A, then this is the equation dx dt is ax. This is an example of linear constant coefficient homogeneous equation, or first order system. This, maybe I'll put a star here. This is going to be the focus of this chapter. So the analytical methods that we use to solve these differential equations, almost all of them will rely on the equation looking exactly like this. Okay. Now, what does this initial condition imply in terms of what you're used to? Well, the solution vector is x1, x2. So this is just saying that x1 of 0, x2 of 0 is equal to the vector minus 1, 0. So this is just a condensed way of saying two initial conditions, one on each unknown function. x1 of 0 is equal to minus 1, and x2 of 0 is equal to 0. That's it. That's all that's being said. So using matrices and vectors is just a nice shorthand or abbreviated way of dealing with this. Okay, of rewriting this equation. Okay. So just like you rewrote a system of linear equations, like algebraically, right? Like something you would talk about in high school. You rewrote that using matrices and vectors, right? So similarly, you're going to rewrite these equations in this way because it's going to make all the analysis we do so much easier. Okay. Now, there is something that happens here that is slightly different, okay, than what happened before, in that most of what we are going to do here is not, most of the material and what this thing depends on is not going to come from the differential equations side of things. It's actually going to come from the linear algebra side of things. Okay, now, it turns out that solving something like star, I'll call this star. And so solving something like star depends more on linear algebra than on differential equation stuff. Now this could be a little bit deceptive. Of course it's going to require a bunch of differential equation stuff, but a good analogy here is think back to homogeneous constant coefficient, like second order equations, for instance. Once I tell you the process for assigning a homogeneous solution to a root of the characteristic polynomial, right? Once you understand that process, then solving a homogeneous constant coefficient equation really just comes down to finding roots of a polynomial, right? So in that sense, once you understand the rules for assigning solutions to each root, then what's more important is the algebra of finding roots of polynomials than the differential equation side of things. Okay, so similarly, in order to solve equations like this, we're basically going to rely on a bunch of linear algebra stuff. Okay, and so this, and understanding a few things coming from linear algebra, which you may have not seen before, depending on whether or not you've had 240 or 461. If you've had 240 or 461, then what I'm going to go over here is going to be fairly easy, or either completely trivial or just a nice refresher. If you haven't had 240 or 461, then what you're going to be seeing here, you'll likely be seeing for the first time, or at least some of it, some of the most important bits you'll be seeing for the first time. And this is all contained in a supplemental section in the online notes. That is, this is section 3 in chapter 3. So because of this, we have to do linear algebra stuff. Okay, so we have to get you up to speed on linear algebra stuff. So the next thing we do is going to be a huge aside. So thus, we need to spend a good amount of time on linear algebra stuff. So if you have already had Math 240 or 461, this will all be trivial. It may all be trivial anyway, but this will definitely all be trivial to you if you have had 240 or 461. Okay, because this was like the bread and butter of those courses. Okay. All right, and so this is contained, so there is a nice supplemental section in chapter 3 of the online notes. It is section 3. It's 3.3. And the title is Supplement Matrices and Vectors. And it covers everything you need to know. Now, it is possible that some of the things I went over before were slightly confusing. If you don't remember how matrix multiplication works, for instance, you might not remember that multiplying matrices works in this way, where I think of like slamming these two vectors together and adding uh, the results in this way. But we're going to go over all of that stuff. Just a nice refresher. This refresher that I'm going to go over is roughly covered in that supplement that I mentioned here. I don't promise I'm going to go in the exact same order, because I'm just kind of go off the top of my head here. But you can have a look at that supplement, and you will find all of that, all the stuff you need in order to do all this. Okay. So, what are the important bits? Um, so, if I have, say, two vectors, right? So if I have vectors u and v in Rn, so these are vectors in Rn. I can't write in boldface with a pen or on a blackboard, so when I'm indicating a vector quantity, I'll try to put this little arrow over it. So u and v are vectors in Rn, which means that, say, u is some column vector, u1, u2, just an array of numbers, n of them, where each of those is a real number. V is some other such thing, so v1, v2, and so on out to vn, where each of the vi's are real numbers. Now the question is, what is the algebraic structure of Rn, right? If Rn is the set of all vectors or n-tuples, whatever word you want to use to describe these things. So these are vectors or n-tuples, or ordered n-tuples of real numbers. In the n equals 2 case, notice that this is actually the same as ordered pairs. So, here. So the example, if u is the vector -1, 2, and v is the vector, say, 5, 0, these are both vectors in R2. Okay. So I can think about these as ordered pairs. This is like the ordered pair, right? Another way of thinking about this is u is the ordered pair -1, 2, and v is the ordered pair 5, 0. Okay. This is a more convenient and nicer way for thinking about it for a lot of reasons, but of course we can just think about these as ordered pairs. I can talk about the algebra that I want to do to these things. If I have two vectors of the same size, they both live in, say, Rn, I can define vector addition of those things. What is vector addition here? Well, vector addition is I just take each slot and add it to the corresponding slot in the other vector, and that is that slot of this vector. So, for instance, this is the vector whose slots are determined from the components of u and v in this way, right? u1 plus v1 is the first, u2 plus v2 is the second, and so on, all the way down to un plus vn. Right? That's how vector addition works. Okay. The other important vector operation is scalar multiplication. So if c is some scalar r, right, then c times u, or sorry, so c is some scalar in r, in the reals. So cu is just the vector I get from multiplying every component of u by c. So there it is. Okay. All right. So let's do it for these two vectors real quick. So for instance, what is u plus v? Well, this would be minus 1 plus 5, which is 4, and 2 plus 0, which is 2. Right? What is minus 2 times u? Well, this is 2 times, and minus 4 is in the second slot. Okay. All right. Now, we could think really quickly. I'm not going to worry too much about this. There's geometrically, what is u plus v? Since u and v can be thought of, there are these column vectors which I can think of as ordered pairs. I can associate to any n-tuple or ordered pair, ordered triple, whatever space it lives in, a point, right? So really, vectors are points and points are vectors. If you haven't seen this before in Calc 3 or something. So points are vectors, vectors are points, so associated to the vector u is the point minus 1, 2, for instance, so it's an arrow pointing this way. I'm going to draw my vectors. This is not referring to these u and v, so I'm just going to call this vector u, and I'm going to draw another vector v. Geometrically, what is u plus v doing? It is finding the diagonal of this polygon, which is actually a parallelogram. This is called the parallelogram rule, if you like. So this diagonal of this parallelogram is the vector u plus v. Similarly, if my vector u looks like this, all right, then what does cu do? Cu takes u and scales it by a factor of absolute value of c, since we said that c is a real number, so it could be minus here, it could be 0 even. And in that sense, if I take u and I scale it by 2, what I get is this thing. Minus u would be the vector pointing in the opposite direction here. Minus 2u would be minus 2u, except pointing in the opposite direction. And so on. In fact, if I consider all scalar multiples of the vector u, I get an entire line in the plane, okay, that is determined by that. This is the simplest example of what's called the span of a vector, okay. Now, a couple of things here in our vector algebra. This tells you the algebra structure of the product you have is this thing, right? Scalar multiplication. The sum is this thing. Of course, now it makes sense to do u minus v, which is u plus minus 1 times v, now that you have scalar multiplication. You can do that. But also, what is the zero object here? It's the zero vector. The zero vector of size n is just the vector containing nothing but zeros. right? And you can see immediately that for such a thing, u plus 0 for any vector is always equal to u. Okay, u plus minus u is always equal to 0. Right, and so on. So there's a whole list of things. Now this thing satisfies all of the nice properties that you might hope. So it's commutative, right? It doesn't matter what order I add these things. It's associative, so is scalar multiplication. I'm not going to get too much into the weeds here, but that's what's going on if you haven't seen this sort of thing. Now, quickly, let's talk about, what is the span of a set of vectors. So if I have a bunch of vectors u1 to un, what is the span of these things? This is the set of linear combinations of the vectors u1 to un. So the set of linear combinations of the set containing all these vectors. What is a linear combination? Linear combination of a set of vectors is something that looks like this. This is a linear combination. What makes it a linear combination? All these are constants. Right, and I'm just adding all those constants times vectors together. So the set of all linear combinations of a single vector looks like this. Now there is a case I could choose a vector u where it's such that the span doesn't look like a line, and that would be span of the 0 vector. So span of the 0 vector would look like a single point, and it would be the point at the origin is what the span of the 0 vector would look like, because the set of linear combinations of the 0 vector is going to be the set of scalar multiples of the 0 vector, but that's always just 0. That's always just sitting here. Okay. But here, the span of u is the set of linear combinations of a single vector u. So it's the set of things that look like this, cu, right, for every choice of c. So I get the entire line here, right? Now, the question of what the span looks like leads to the notion of linear independence. So it's a little tricky when you first start out because you say, okay, span of 0 is just a single point, but span of u is this whole line. So then you think, okay, what about the span of two vectors? What does that look like geometrically? Okay. Well, there are options, right? So if neither of the vectors are 0, it still might look like a line. And it would look like a line if u and v are scalar multiples of each other. Okay, because you're not getting any additional info, right? So what can span, so let's let u and v not be the 0 vector. So neither of them is the 0 vector. What does span of uv look like? There are options. Sometimes it looks like a whole plane. So sometimes I have a vector u and I have a vector v, and they span an entire plane where u and v are the axes. So that everything can be written as two constants, right? C and d. So c times u plus d times v. This is a linear combination of u and v. And anything in this plane can be written as sum like this. But sometimes when you look at the span of u and v, what you get is not a plane, you just get a single line. Well, when do you get that? This is if u is equal to cv for some c. Why? What happens? Well, what happens is when you go to form a scalar, when you go to form, say, a linear combination, cu plus c2v, because u is cv, you get c1 times cv plus c2v. And so what I get here is c1c plus c2 times v. So really, I don't get two vectors worth of directions. I just get one. And the reason why is because u depends on v in this with this relationship. Okay. It is somehow not independent of v because it is a scalar multiple of v. And so actually I only get one dimension's worth of info here, of data, and that is the v direction, right, is all I get. And so it's a constant, whatever this is, it's just a constant. I'll call it big C times v. And we know what that thing looks like. It's just a line. Okay. Now, in the case of two vectors, you could say, oh, this is determined by whether or not they're scalar multiples of each other. That's true. But once we move to the picture involving three variables, or three vectors, I should say, then this is where linear independence comes from. Because now it is possible that none of these are scalar multiples of each other, and yet the span of these three vectors is just a single line. Okay, that can happen. All right, and so we need linear independence. Now, there's multiple definitions of linear independence. I'm going to use one that makes sense for us in this course, and the one that's going to make sense for us is going to come from the determinant. Okay, so for us, uv, maybe I'll write it like this. u1, u2, and so on, to un, are linearly independent if the determinant of A is non-zero, where A is the matrix whose columns are u1, u2 to un. So this is the matrix with columns u1, u2 to un. Now, we have to define what determinant is in that case, right? So the determinant of a 2 by 2, which we went over, we know this is AD minus BC. How do I compute the determinant of a 3 by 3? So you can look at supplement or calc 3. I'm not even going to write it out here because we're not going to need it directly. Or calc 3, 240. If you want to see how this works, you did it in calc 3 for the cross product. You needed to compute the determinant of a 3 by 3. You can, of course, define the determinant for any square matrix. That's how this works. This matrix, this is a perfectly fine way of specifying a matrix. Okay, there's absolutely nothing wrong with specifying a matrix like this, but typically the way that a matrix is going to be written is the following. So a matrix A is an m by n matrix, right? This is m rows and n columns. And the notation we typically use for a matrix like this is the following. So the entries are written like this. This is the entry in the first row, first column. The entry in the first row, second column is A sub 1, 2. So these subscripts are, this would be A sub 1, 1, A sub 1, 2. This is not A sub 11 and A sub 12 here. Then in the first row, third column, this would be A sub 1, 3, all the way over to A sub 1, n, because there's n columns. Okay, the next row would be A sub 2, 1, because so this entry is in the second row, first column. The next entry would be in the second row, second column, so A sub 2, 2, A sub 2, 3, and so on, all the way out to A sub 2, n. And going all the way down to the mth row, this is A sub m1, because this is in the mth row, but first column. This would be A sub m2, A sub m3, all the way over to A sub mn. This would be how I write my matrix. Another way, an equivalent way of writing it, is this is A sub ij, where I goes from 1 to m, and j goes from 1 to n. So A sub ij is the entry of A in the ith row and jth column. Okay. Now next time I'll go over matrix multiplication and some basic matrix algebra stuff, and we are going to get as quickly as possible to eigenvalues and eigenvectors of a matrix, because that's going to be our main the main thing we're after, because it turns out that is going to be exactly what we need in order to solve these systems. And you're going to see how this ties into what we did before, for not for systems but for just second order equations. But anyway, that is that for now. So we'll pick up here tomorrow, finishing our review of linear algebra stuff. So anyway, I will